Cool. Well, thanks everyone for coming. My name is Jeff Chow. I'm the co-founder and CEO of Sync Computing. Thanks so much for coming. Today I'm going to talk about best practices to managing Databricks clusters at scale to help lower costs. I'll also talk about what we're doing here at Sync to help kind of solve this problem as well. But hopefully you'll kind of have some takeaways about what you all can do at your organizations on making your compute and Databricks experience more efficient. Um, just a quick agenda. I'll give a very one-slide introduction into who I am and who we are. Who am I to talk about this stuff, and what is my experience? So I'd love to talk about that. And I'll talk about kind of the top 6 things we've seen at other companies, and then I'll talk about what we do here at Sync and our product with Gradient, and we'll kind of do a little under the hood explanation in terms of what we do within our product. So a quick little intro to who I am and who we are. We're a spin-out out of MIT. We have a very technical background. We come from kind of the high-performance computing space, so we've kind of always lived in the cluster world. And our big mission is to enable this thing we're calling declarative computing. And this idea is basically where compute is provisioned based only on the output performance, meaning you don't have to select instances or number of workers and all that stuff or memory. You just tell us the output. You say, I want this runtime, I want this cost. Some other magical system go figure out how to do that. That's kind of the big vision of what we'd love to do. Our application today is in the Databricks ecosystem, but as you can tell, that mission isn't really Databricks specific. A quick company timeline for us, we have a bit of history, but in 2022, we focused solely on Databricks, and around then, we started working with a bunch of companies in various capacities, and in 2023, we kind of built our first MVP. We worked with a bunch of companies, like 50+ companies, kind of getting our feedback, trying to figure out, okay, how do we control your clusters? How do we optimize it? What works, what doesn't work? It was a lot of iterating. It's a very hard, complex problem, which I'll kind of get into. And then earlier this year, we finally released kind of our flagship product, Gradient 1.0, which is kind of the end result of almost 2 years of research in terms of how do you actually optimize someone else's infrastructure, and you want to make sure you're doing it safely and conservatively. Just some proof points. Since January, we've had a bunch of great successes with a bunch of large customers. These are kind of the actual cost savings they've gotten on their actual jobs. So it's ranged from 20% up to 63% on kind of real production jobs that users have. So hopefully you're convinced that I know a bit about what we do and how to actually optimize Databricks. So these are kind of the 6 main ones I wanted to talk about. These are a bit more advanced than kind of your basic stuff, but just to quickly go over them, the most obvious one is optimize your cluster instances. This is probably very straightforward. And I know this morning they talked about serverless, so we'll talk about that. Like, how does this all relate to serverless? That's probably a big question a lot of you all have. A couple other things like photon and auto scaling. You need to A/B test these things. Optimize elastic block storage. That's an AWS specific setting. So if you're on Azure or GCP, I apologize. Understanding the risk of spot instances. Spot isn't all that it's made up to be, and we'll kind of talk about why. And then understanding how serverless works. And then knowing when to use all-purpose compute clusters. These are kind of the big 6 takeaways. So let's just march down the hill. So the first one is optimizing compute clusters. This one is by far the most sensitive. This one directly impacts your costs. What I'm talking about here is selecting your driver and worker instance types, number of workers. Unfortunately, the vast majority of companies we work with pretty severely neglect how to do this. Most companies just kind of have a stock recipe, or they copy the previous job, or they have these guardrails to prevent their engineers from provisioning too many workers or using too big of a cluster. And it's very kind of rule-based. The one kind of medium good solution we've seen across companies is kind of these buckets, if you will, like kind of small, medium, large, and they're kind of like prescribed clusters so that your engineers can't go crazy. That's kind of, again, these are more like human engineering solutions, and there's nothing really technical about like what is the mathematically best cluster for your job. 2 is photon and auto scaling. So I'm a big fan of photon. I think it's awesome technology. Quick explanation: it's some awesome kind of a expansion of Spark. It's like a C++ expansion to accelerate some of the kind of very CPU intensive workloads they can run with some of your SQL queries. And auto-scaling is kind of an auto-scaling policy to kind of scale your cluster up and down. The main problem, though, is that Photon and auto-scaling, as promising as they are not guaranteed slam dunk wins. They are extremely workload dependent. And unfortunately, the answer is very uncool. It depends. And so I recommend you need to A/B test. That's kind of the only real way you know if Photon and auto-scaling are really worth it. And the penalties, especially for Photon, is that they charge you double the DBUs. So if you're in the case in which Photon doesn't help, you're actually paying more money for no real acceleration. So my recommendation is you have to always A/B test to make sure that your workloads are benefiting from there. Let's zoom in a little bit into auto-scaling. So what is the issue with auto-scaling? That sounds pretty straightforward. So this is a blog we published a little while ago, kind of analyzing auto-scaling. And auto-scaling as a concept is a pretty universally understood concept. You measure some sort of utilization metric, and then you scale. You add a worker when you cross some threshold, or you remove a worker when you're below some threshold. The problem is kind of summarized in that graph over there. So on the y-axis, you have number of workers. On the x-axis is your job runtime. And you can see what's going on in auto-scaling in the red curve. By the way, this is the TPCDS benchmark, 100 gigabytes. What's going on is the red curve is showing you the workers that are being added and removed. And the big problem is every time you add a worker, it requires a couple minutes of spin-up time, right? It's like installing libraries, pip install, et cetera. Unfortunately, you're paying for that couple, like 5 minutes every time you add a worker when you're not adding any more processing power. And so because of that, there's an unfortunate tax whenever you're adding and removing, mostly adding workers. And that tax can add up. And as you can see in that red line, it's just kind of going up and down, versus the black line, which is just a kind of boring old static cluster, 2 workers. You can see it just kind of gets up there and it chugs and then it shuts down. And it actually finishes faster than auto-scaling, and the area under the curve there is roughly the cost. You can see it's actually much cheaper. And on the right there, you can see actually the cost versus the various different auto-scaling and fixed clusters. I think the 2-node one, sorry, the captions here are blocking it, but the 2-node one was about 37% cheaper than auto-scaling 2 to 8, which is like the default one. Again, this is very workload specific. I'm not saying this is gonna apply to all your workloads, but you have to kind of A/B test. I recommend if you have kind of static jobs, like ETL jobs, where they're just kind of chugging, static clusters might be more optimal. Auto-scaling is great if you have kind of ad hoc workloads, or if your workload for some reason pauses or has to wait for something and you have like a long idle time, then I think auto-scaling is great. But if it's just like a pure ETL job and it is just chugging, probably a static cluster is best. Photon is really interesting. So this is our benchmarks. We've kind of reproduced Databricks' tests with Photon on TPCDS. So we do confirm that their kind of marketing materials are correct. You do get about a 2x speed up with Photon and TPCDS. So that's great. That graph there shows you the DBU cost only, not the cloud cost. And the x-axis is runtime, and those kind of salmon colored dots are Photon. So you can see it's shifted to the left, meaning it's, relative to the black and green dots, it's about a factor of 2. So we'll give Databricks that. Unfortunately, it's not lower. And that's because, yes, it is 2 times faster, but they doubled the DBU cost. However, that's only the DBU cost. And so they do get points for lowering your cloud cost, because let's say you're running that on AWS, your cloud cost did actually go down as well. So their benchmarks are correct. We validated that they're great. The only problem, and something I think Reynold mentioned at the keynote, was that benchmarks do not mimic your actual workloads, as everyone here knows. They're nice, but the odds of your workload looking like TPCDS are very low. TPCDS is an accumulation of like 99 example queries. Like, is that what your ETL job is? Probably not. So of course, Photon is kind of it might be good, it might do nothing. And I pulled some quotes from the actual Databricks original paper that talked about Photon, and even they admitted, Photon is great for CPU intensive workloads, but it's not so great for queries that are kind of IO or network bound. So again, with its 2x DBU cost, you should really do some A/B testing to make sure that it makes sense. Next up is EBS setting. This is an AWS specific setting. So EBS is elastic block storage. And this is a very nuanced technical setting. Probably most of you don't even bother trying to change these things. I don't think we've ever met anyone who actually optimized these settings. People just kind of pick default values. In reality, it's kind of the same case where sometimes it actually has a huge impact. So this is a great study that Sean did over here, where we looked at different workloads. So each one of these boxes is a different kind of test job that we ran. And the different colors of the bars are the different settings, like blue is default, orange is optimized, our optimization, green is disk attached, red is their Databricks is auto scaling. And you can see in the top 3 jobs, they're all about the same. It doesn't really matter what you picked, so that's fine. But then on the bottom 3 jobs, there was a huge impact. The one on the bottom left-hand corner was 80% faster if you actually optimize the EBS settings. So again, it's same case with like Photon and auto scaling. It's workload dependent. Like, what do you choose? Unfortunately, for these ones, these are much harder because you have to put in integer values. It's not just a checkbox. So optimizing EBS is horrendously annoying, and probably no one in this room actually spends time trying to optimize EBS. But it may or may not have a huge impact on your workload. This one is a little bit higher up. This is kind of one we've discovered working, especially with large enterprises with like lots and lots of jobs. I would say people using all-purpose compute clusters, perhaps not appropriately because of the cost difference. So probably most people here know all-purpose compute clusters can be extensively more expensive than jobs compute. But if you're just doing the same thing, like you're just a scheduled APC job, and there's no reason why you should be using APC clusters, you're just paying a lot more money for no real reason. It's a mistake even we've had in our own environment. Sometimes people just forget, or you pick the wrong thing and you go, oh shoot, this was not supposed to be an APC cluster. And just for a comparison, this is from the Databricks website, their kind of cost calculator. With identical clusters, the APC job is $5.50. The jobs compute one was $1.50. That's a 3.6x cost difference for the exact same hardware. So it's just something to be aware of. But if you need APC for your application, if you have like ad hoc compute or it's a shared compute and a bunch of people sharing your compute cluster, then by all means, APC is great. But if it's just this job that's chugging away and you don't really need the features of APC, I recommend try to migrate to jobs compute. In general, jobs compute is great. If you look at all the suite of products that most people use, jobs compute just on a $1 per DBU rate is much more efficient than the other compute ecosystems, even like SQL warehouses, APC, et cetera. And again, you have to kind of determine, is your workload, should you migrate your stuff to jobs compute? Maybe that is a more economical solution than kind of using SQL warehouses or APC compute. So it kind of depends, but if your SQL warehouses are more for like kind of these ad hoc queries, then jobs doesn't make any sense. But it's just, everyone should just be aware that jobs is by far the most economical compute that there is. The 5th point is understanding the risk of spot instances. This one is also very nuanced. I think most people kind of assume if you use spot instances, oh, that's a guaranteed 90% cost savings. In reality, spot is quite dangerous for specifically distributed workloads like Spark, because if even a single worker is revoked randomly, depending on what your job is trying to do, that could have catastrophic effects to your job. It could kill your job, or your job is now trying to repair some of the damage because it basically just yoinked a worker randomly and it has to go back and figure out, how do I repair this job? And what we've seen, this is from our products dashboard, the top graph is cost over time and the bottom one is runtime. And you can see, so we're not doing anything. This is just kind of in monitoring mode, but you can see like the 2 spikes there, those were due to basically Spot coming in and yanking workers, and the runtime and cost ran up by 2x. And so the question is it worth it? It depends on average, and it depends on your workload, and it depends how sensitive your job is to Spot. So this is something most people are kind of surprised to learn. Oh, there's some risk to Spot, and perhaps your overall cost savings is not. It's almost never 90%. It's probably maybe 10 or 20% is kind of what we've seen. So that now a big question, serverless. So serverless is a new thing. Clearly Databricks at a high level is moving everything to serverless. I think we would all love not touching these knobs. And I think Ali probably also wants to get rid of all of these knobs. Everyone should just go to this beautiful serverless system. So I thought it'd be worth spending some time just at a high level. What is serverless? Of course, yes, there are servers, but at the highest level, this is kind of the big difference. So on the left here, you have the classical system. And the basic idea is you still have two systems. There's your cloud, like your AWS account or Azure account. That's where the cluster is living. And then you're connecting to the Databricks side, which is kind of orchestrating and managing your cluster remotely. And of course, your total cost of ownership, you get two bills. One bill is from Databricks, that's the DBUs, and then the other bill is from Amazon or Azure. So you always have two bills. The big pros of Classic, it's fully controllable. You have full visibility. You know exactly what's going on. You can leverage your own cloud contract. So if you have like a 40% discount deal with AWS, that's great. Plus another discount deal with Databricks, you can kind of leverage combo contract deals. And because you fully control the infrastructure, you can really fine tune and optimize your infrastructure because you have full visibility and control. The cons, sorry, it's blocked by the text there, but the cons are it's annoying to tune infrastructure. I don't think anyone here enjoys tuning and tweaking your cloud infrastructure, like number of workers, memory, etc. And two, spin up time is really painful. I know that's a huge pain. Everyone hates waiting 5 to 10 minutes for your clusters to spin up. But if it's a scheduled job and it's going to run at like 3 o'clock in the morning or 12 o'clock, then do you care about a 5 to 10 minute spin up time? Probably not. But for interactive clusters, or if you need something faster, or if it's a really short job, then spin up time is really painful. Serverless, on the other hand, over here is a much cleaner system where now you're not running anything in your cloud. All of the compute lives inside Databricks. And so now you only get one bill. And so the charge from the DBUs is basically everything. It's the compute plus the DBUs, it's everything. You don't have to worry about anything. And the huge pros, the huge advantage, obviously, is you don't have to worry about all that stuff that I just talked about. EBS settings, number of workers, photon autoscaling, that's all gone. That's all swept under the rug. And you just submit, run, go, and you're good to go. And I think that's kind of the big strategic direction that Databricks is going to go, at least based on the keynotes, that's where all like the latest features are going to go. And so there's definitely probably the long-term big direction of serverless. And personally, a huge win is also no spin-up time, or a very short spin-up time. So I think Databricks has done a great job in terms of shrinking the spin-up time for all of these serverless warehouses, serverless jobs compute. The cons are that Databricks controls the pricing. And so now you don't really see what the compute is, and the bill you just kind of get afterwards. And the question is, do you agree with that bill? I think that's going to be kind of tricky, especially if I know like jobs compute is new, that you get billed afterwards and you don't know what kind of cluster they spun up to run your job. Maybe it's a baby job, but they spin up a huge cluster and then you're going to pay for that. So does that make sense? And two, you can't fine tune anything. Like it's completely black boxed. So you can't tweak any of the infrastructure. In my opinion, it's more in like the Snowflake world. Snowflake is similar, right? Snowflake is totally black boxed, and it seems like these two companies are kind of going in that direction. They just want everything black box, and I think the heart is in the right place. They just want to make it easier, easy, right? Get rid of all of these knobs, but there is some sacrifice, right? You lose a little bit, and it kind of depends on what you all care about. So a couple interesting studies that we ran. This is one we ran on SQL warehouses. This is, again, serverless SQL warehouses. We ran the TP-CDI benchmark with dbt. And the left is runtime versus the different warehouse sizes, and the right is cost versus the different warehouse sizes. And one of the questions is always like, well, what warehouse should I use? And for this particular workload, you could see from 2x small to medium, it's scaled. You're in it's called the linear scaling regime, meaning when you double the compute, your runtime got cut in half. And so if you look at the cost curve, those 4 bars are about the same. So it didn't really matter what warehouse you picked, which is true. But after medium, the runtime benefits stop, right? The runtime just plateaus. Those orange bars to the right are about flat. Something weird happens at 3x large. It gets a little bit better. But you can see on the right here, your cost starts skyrocketing because there is no more scaling advantage. This is a very fundamental computer science concept called Amdahl's law, where basically any large-scale computing system that you have eventually stops scaling. And it doesn't matter how much more compute you throw at it, you're bottlenecked by something, usually like network, memory, CPU. Something is killing you, and adding more workers and nodes doesn't do anything. And this is just a fundamental concept that's true, whether you're serverless or manual. No one can avoid this. This is like a law of nature, and it's true in serverless as well. And so that's kind of my summary of basically what all of the different tips that we've seen in the Databricks ecosystem. And so I wanted to kind of take a step back and talk about, what do we do? How are we helping to solve this problem? And probably the big question is like, what is our solution? How does it relate to serverless? So I want to take one really high level step back and go back to that declarative computing concept that I mentioned. This is kind of the big kind of more academic idea that we would love to see the world turn to. And so the basic idea is this is the world today, right? This is not Databricks exclusive. This is like all of computing. So you have your code and your data, and you also have to specify the compute resources. You have to say what you need, right? You submit that, the cloud spins it up, you run it, and then the output is always this stuff: the cost, the runtime, latency. If you're doing even AI ML stuff, accuracy, like that's usually an output. And so the question is, why can't you just flip it? Why can't you just insert or input the output? Why can't I just say minimize cost, my runtime max 1 hour, latency 100 millisecond, something else in the middle, go figure out what cluster that is, and then ideally the output then matches the input, and then you're kind of in a great spot. This is kind of the high level idea of what we were trying to do here at Sync and what our product does, Gradient. We want to be that magical middle layer that kind of figures out what is that cluster that hits your thing, hits your goal. That's kind of what we want to do. So how do you do that? So at a really high level, this is what we built. And so this is kind of, again, the idea. You submit your stuff, you spin up a cluster. And the thing that we are adding is basically a feedback loop. So I don't know if those of you who did like control systems, but this is basically like a real-time feedback loop that every time your production job is running hourly, daily, it takes the output and feeds it back. And you can use that information to train a machine learning model to kind of figure out, this is the best infrastructure for your job. And ideally what this looks like is, let's say, again, this is the use case here is like production jobs that are running over and over again. And so ideally what happens is every time your job is running, like once an hour, let's say, the ML model is learning and it's saying, this is the right, that infrastructure wasn't great. Let me try this one. Oh, this is good. Oh, that wasn't that great. I think you can do better. And ideally it kind of walks your cost down, or whatever your goal is, to kind of to try to hit whatever goal you have. Cost is usually the number one thing people want. So that's kind of a big one. So the idea is that is what we are adding to kind of the Databricks ecosystem, is this feedback loop. We will actually go in and actually monitor your job, and then we'll actually change your cluster for you. So it's an active solution. It's not a passive thing where we kind of give you a list of recommendations. We actually want to be active and in the loop and kind of train these ML models. So that's kind of the high level idea, and it sounded kind of academic, but it's actually real. It's true. We built it. It's available today, and people are using it. And so this is an example from one user. You've kind of already seen snippets of our product, but the top graph is cost. The bottom one is runtime. And here's an example, the orange curve here. Let's see if my mouse works. This is the orange curve where we switch it to an on-demand cluster. And this is one of their production runs that runs hourly. And you can see that as it kind of runs, our ML model trains and it starts to optimize. And in this case, it did both. It got it cheaper and faster. And it actually did it by going to a larger cluster. So it's not so simple as just slash your cluster in half and you can do it. Actually, sometimes a bigger cluster is what you need, because maybe you're IO bound or something like that, and you need more nodes. But this is a real run of a real production job that a user used. This is another one. This is an internal test job to kind of show auto scaling. So I talked about auto scaling. What do you do with that? That's kind of annoying. Should I use auto scaling? Should I not? Here's an example of Gradient kind of figuring it out. So we started with kind of base auto scaling configs, 2 to 20 workers. And then after the model trains, it figures it out. And then it realizes actually fixed 2 workers is best. And here we got 58% cost improvement over auto scaling. And so again, here we're piggybacking off of your production runs. You're doing these runs anyway. So why don't you use that information to kind of inform your infrastructure and figure out and improve. Again, this is all automatic, so you can go have lunch, you can go to sleep. Gradient is kind of working behind the scenes, figuring out what's best. This is the EBS, the elastic block storage optimization that we have. So this is another customer Forma. So this is another real example where, again, we optimized the EBS settings and we got 18% cost savings, 19% speed up. We actually optimize settings that aren't even available in the Databricks UI. You have to go and use the Databricks API to optimize some of these settings, like volume IOPS and volume throughput. And we basically showed that even with those low-level settings, you can get pretty significant cost savings pretty quickly as well for your job. And of course, everything I've shown you is very like cost sensitive, cost related. But the other big advantage is, Gradient is more of a management system. And so here we can actually control the SLA. So this is a really interesting example where this dashed line is actually the SLA that a user can set. And so here we dropped the SLA, so we wanted something faster, right? Maybe your business goal is I need a job that runs a lot faster. We can set it down here, and what Gradient does is it'll find the cluster that eventually hits that runtime. And you can see the consequence was that we needed a kind of a beefier cluster, something that cost more. But now you kind of have the business intelligence that like, oh, okay, yes, I can hit my SLA. It cost me, 2x more. And you now can make that business decision of, was it worth it? Do I care about an SLA that much? Or do I prefer cost savings? Then you can increase the SLA and go back to a much cheaper cluster. So this kind of control is really what Gradient's all about. Like you just set the end goal. You set the runtime, you set your cost goal, and Gradient will use your piggyback off of your existing runs to kind of optimize. So this is probably the big question. This is a quick study that we did last week. It is only a single data point, but we did take one of our test jobs and we had to migrate it to serverless for job serverless. And job serverless is still only public preview. So it's still an early product. I'm sure it'll get better over time, but we did kind of a quick test to see, how do we compare against serverless? That's kind of the big question. We were very curious as well. So we took our test job and we ran it on serverless, and we got a cost of a little over $3. And we took the same job and ran it on Gradient, and Gradient was able to beat serverless from a cost perspective, and we got 65% cost savings using on-demand. And if you use spot clusters, you could get a squeeze out a little bit more. We did have to increase the runtime. So our runtime was about an hour, and serverless was about 30 minutes. So I think that's pretty impressive from serverless perspective that they could get really good runtimes. They didn't have that spin up, spin down time problem. But this is just an example of what Gradient does behind the scenes. It is aggressively trying to find you the cheapest cluster possible. And just a caveat, I understand serverless is still early. It's still under public preview. I'm sure they're going to improve the algorithm. So I expect that red line to go down over time. But for now, you can kind of see the difference between what we're trying to do and what's available now in kind of serverless jobs. So in the last few minutes, I can kind of show you a quick little demo of what our product does. So this is Gradient. This is our SaaS platform. The first step is always like, what jobs should I even optimize? So this is our Discover page where we actually go into your system and we'll go find kind of your top most expensive jobs and kind of identify for you, hey, what jobs should I even use? What should I try to optimize? And then from there, this is kind of our summary page. This is just our demo account, but here we can kind of show you a high-level ROI, like what did Gradient do for you? How much cost savings did we get you? How much are you spending? This is kind of the big management screen. And then within the page, within a single project is basically one job that we're optimizing. So this is the optimization of one job. And so we actually have custom ML models for each job. So if we're managing 1,000 jobs, we have 1,000 ML models. We treat each job uniquely. We don't apply kind of blanket heuristic rules or guardrails. Each one is unique, and we treat them uniquely. And so you're all already familiar with these graphs, but something that our users really like is we also show a timeline of Spark metrics, because you want to know what changed last week or what changed 2 weeks ago. So we show you core hours, number of workers. Input size, this is a big one that usually fluctuates a lot. It's just a test job, so we don't see it here. But we can see like disk spill as well. So you can kind of see and monitor what actually changed as you kind of modify the cluster settings. Okay, so in the last few minutes here, I can kind of go over what are we doing? Like, what is Gradient actually doing under the hood? I keep on talking about this mysterious ML model. So what is actually happening? So here, we're gonna kind of peel the layer back one bit. We can kind of see what's actually happening. So on the top here, this is actually a real user's job, where the top graph is runtime. This second one is the actual cost of the job. And these two are basically what you can actually see what Gradient's actually changing. So here we're changing the worker count, we're changing the size of the workers as well. You can see the algorithm is basically trying to navigate and trying to figure out what is the best, cheapest cluster possible. So it's kind of going up. The impact of the cost kind of goes up and down as it kind of trains. And then eventually it figures out, oh, okay, we mapped it. We understand what your cluster does. And then boom, we get you the cheapest cost. Here we got them 65% cost reduction. Again, this is a real user's production job. So that was really great to see. Another use case that may be relevant for you all is more of a variable data size use case. So this is one, it's a job that runs hourly. And you can see by the top graph, it kind of has this sine wave profile. That's because during the daytime, the data size is much bigger, and at nighttime, the data size is much smaller. And so the orange line you see is actually our model kind of fitting to that. And so what we do is we can actually start custom training our model here. And now, given the time of day and the data size, we will actually prescribe a specific cluster for that time and for that day. So you're always optimal throughout a 24-hour cycle. And so this again is not auto scaling. We're actually prescribing a fixed cluster for each hour. So it's completely optimal for this kind of varying data size. And so this is a very popular use case because a lot of jobs aren't static. They're not just like everything is kind of very stable. Sometimes you have data sizes that vary all over the place. And so that's kind of a great use case for Gradient. And kind of where we're going next, this is kind of an internal test, but what we're going to release pretty soon in the next month or two is basically increasing kind of the search space. So everything I've showed you before is the number of workers and the worker size, meaning like 2x large, 4x large, 8x large. And what's coming out next is basically cross-family. So now we can go from like memory optimized to compute optimized and really get aggressive with our search and try to find you that mathematically the best cluster for your job. And in this example job, we got like 85% cost reduction. And so we're aggressively going to continue to expand our search space to kind of increase the efficiency that we can get for our customers. So that's it for my talk. The big key takeaway, if there's one thing you all can learn about kind of any cluster setting, is that it depends. Everything is workload dependent. There are very few global rules that apply to everything. So I really recommend if you all go back, try to A/B test, see what makes sense. Like, does it work or not? And then, of course, I presented what we do. So if you all run, our kind of prime use case are companies that run lots of jobs, like 100+ jobs a day, and you have a scale problem. Like no amount of kind of consultants can come in and optimize 1,000 jobs a day. And so that's when you need automation. And that's kind of our sweet spot. So if this looks interesting, we'd love to get your feedback. We'll be here. Thanks for your time.
Awesome. Thank you so much.
Thanks all.